Okay, so with 10.3 day 2, we're going to just go through basically what does a write-up look like for a hypothesis test. So confidence intervals, you had a certain thing you had to do. The big thing that changes is that testing section. Because now we're actually testing at 2 hypotheses as opposed to just doing an interval. But the conditions are pretty much the same, except for number 3. So like your conditions, number 1 will always be, we're going to start with proportions only. So like your quiz will have proportions only on it. 10.4 has means, but we'll get to that. That'll be on the test. So condition 1 is that p hat is from a random sample. Okay, that's always condition 1. Basically, whenever we do a hypothesis test or any kind of write-up testing, number 1's always, is it a random sample? 2 is the same condition as a confidence interval. That was number 26 in the homework last night. Check n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So this is condition 2. So then you write our sampling distribution is approximately normal by the central limit theorem. Or the population distribution can be approximately normal, but that doesn't happen as much in a proportion. This is more for means. You got to be careful because like now that we're in testing, there's p and p hat. You want to use p here, not p hat. So it gets a little bit confusing which numbers to do, but we're going to do 2 examples today, so hopefully that'll help you. 3 is going to be the type of test. So before we had a 1 proportion z interval, now you have a 1 proportion z test. So really the only thing that changed is that last word. We're doing a test instead of an interval. You always know when you have a test when you have a ho and a ha. There's no ho and ha, it's an interval. And then condition 4 is defining your parameter, so it's p equals the true proportion of whatever. And again, that'll be in the problem. So the conditions, besides number 3, are all pretty much the same. So that's why if you did well in the Chapter 9 test, you should be fine. Now, for the testing section, this is where things change. The first thing you want to do is list your 2 hypotheses. So remember, the null hypothesis is always that p will equal some hypothesized value. Okay, so what are you actually checking? Is it a majority? Then p is 0.5. Is it 60%? Then p would be 0.6. That will be given to you somewhere in the context of the problem. And then your 3 alternates are either p is greater than, I'm just going to do HV for hypothesized value, less than, or not equal to. Now you also need to write out what kind of test it is. So this, if it's a greater than, we call that a one-tailed right, because, I'll get down there. You want to list your sample data. Just like we did with the confidence interval, you got to list your sample data. So for proportions, you got to give me p hat equals n x. Now, you don't have to give me a z star, because that only works for confidence intervals. You do have to give me an alpha value. Okay, if there's none listed, you got to think about what error would be worse. Or you could just pick one. And most of the time, if there's not one listed, it's greater than or less than all 3. So this is the annoying part. You have to draw the type of test. It seems weird, but that's what they want to get full credit on it. So a one-tailed right is when you're looking at, is the proportion greater than my hypothesized value? So you draw yourself like a little mini normal curve. And one-tailed right, you got to shade in to the right. Because what we're trying to do is what's going to be down here is our test statistic that I talked about yesterday. You basically fill in what your z-score is. What do you get? So usually so whatever you get in your test statistic. If it's a one-tailed left, that means you're looking at a less than situation. So you draw yourself a little mini curve, and then you give me z equals whatever you get for your test statistic. It's just to help you visualize kind of what you're actually doing. And then the one that is tricky is the not equal. That's called a two-tailed test because you don't care. You're looking at both either greater than or less than. So you draw yourself a little mini curve. And what will end up happening, you will get a z-score that's either positive or negative. But you have to give me both the negative whatever and z equals the positive whatever. When you do your actual test statistic, you'll get one of those two versions, either the less than or the greater than. If it's a two-tailed test, you got to put in both. Okay, so if I was grading this, the conditions are still 4 points. The testing section, this is 1 point. Listing your data and drawing your test is 1 point. And then we'll get to the formula and stuff. Yes, Hannah?
Can you explain the alpha part?
So remember, alpha is basically the probability of type 1 error. So it's basically what we're going to look at our p-value against. Remember, if the p is low, reject the hoe. So if the p-value we get is less than this, it's basically what we're going to base our conclusion on. But I would say most of the time this is given to you in the problem. Okay, so the next page, you then have to do a test statistic. So that testing section becomes super long. So you have to show me your test statistic. Here's your formula. So p hat minus p divided by the standard deviation. I want you to use numbers. And then once you get your test statistic, use your formula sheet, or I'm going to show you how to do it in the calculator. Calculate your p-value. And then you basically write a conclusion statement. A z of whatever gives us a p of whatever. Compare your p to your alpha, and the p-value is either less than or greater than the confidence level. Remember, that's your alpha value. There is either evidence to reject or fail to reject the claim that the proportion, whatever. Then you have to give me a second sentence. So usually it starts with, it appears. So the first sentence of your conclusion is like, do you reject, do you fail to reject? The second sentence is, okay, now what are we actually concluding? That the proportion is greater than, or the proportion is still 0.5 or something like that. That seems like a lot. Let's do a problem, and all this stuff will make sense. But again, you're going to be doing these for a long time, so you'll get it eventually. Because your last test in this class is 5 of these. And it's my goal. Everybody's got to get 60%. Okay, and they're usually always worth 10 points. So, let's try the first example. According to a recent article, 43.6% of the 149 18 to 19-year-olds in a random sample have been asked to buy cigarettes for an underage smoker. Is there convincing evidence that fewer than half of the 18 to 19-year-olds have been approached to buy cigarettes by an underage smoker? So, this is 43.6. This is your p hat. The half part, this is your p-value. Fewer than half. So you got to make sure that you understand when you're doing these that you have two different proportions. So let's start with the conditions. So number 1, do we have a random sample? Yes. So p hat is from a random sample. Now, here's where things get tricky. Condition 2, you're checking times 0.5, not 43.6. Okay, it's always n times p. So we're going to do 149 times 0.5 has to be greater than or equal to 10, and 149 times 0.5 greater than or equal to 10. Because you got to do like, I'm pretty sure that's greater than or equal to 10. So, shoot. Those are both greater than or equal to 10. So then we can say our sampling distribution is approximately normal by the central limit theorem. You guys pretty much already have that down from chapter 9. Like I said, the biggest mistake people make in this condition on the quiz and test is they use the 43.6 instead of the half. So, everything that you're going to do this weekend, tonight, is going to be a 1 proportion z test. Because that's the only one you know so far. So, p is going to equal, and then it's going to be in your problem somewhere. The true proportion of 18 to 19-year-olds who have been asked to buy cigarettes for an underage smoker. Oops, sorry, sir. Good so far in the conditions? Like I said, really not much of a difference. Okay, here's where things are different. So the first part of your testing, I need to see a ho and a ha and a visualization of that in the name. So here are null hypothesis. We're assuming that it's 50-50. P equals 0.5. We're trying to prove that fewer than half. Okay, we're trying to prove fewer than half. So that means my alternate is P is less than 0.5. So this test is one-tailed left, and I draw myself a little picture because we're doing a less than, and I'm going to leave this z blank for a minute. Once I get my actual number, I'll put it back in. So you give me the ho, the ha, you name it, you draw it. All that kind of goes together. Okay, so then you list all your stuff. So p hat was 0.436. We don't have an x because it automatically gave us the p hat. N was 149. We got to pick an alpha value. So there is no alpha value. If you think about your type 1 error, type 2 error, type 1 is rejecting this when it's actually true. So saying it's less when it's really equal to 50%. Type 2 is saying it's equal when it's really less than. Really, type 1 error is worse. But I know the answer, and I want a certain conclusion, so I'm going to make alpha 0.1 for now. I think on your homework, if you check the half sheet, do they give you alpha values? Yeah, they do. Okay, so then you don't really have to think about it. And like I said, on the AP test, it'll either be greater than all three or less than all three if they don't give you one. Anyway. Okay, so then you do your test statistic. So we got z equals So it's p hat 0.436 minus p 0.5 divided by the square root of p, so 0.5 times 0.5 divided by 149. This is the other thing people always screw up, is they use that 0.436 in the standard deviation. Literally the only time you use p hat is at the beginning of your formula. Now, you can do this by hand, or can I show you how to do it in the calculator? Because it's way easier. So, in your calculator, every test we do is in the calculator. You still have to show the formula, though, to get full credit. So, go over to tests. We're doing a 1 proportion z test, so test 5. 1 proportion z test, so test 5. So your p sub 0, that's your ho and ha. That's your ho and ha, so 0.5. Now, in the calculator, you have to give me x over n. So, like, I can't put in, for x, I can't put in 0.436. But I can do 0.436 times 149 to get the actual x value. Here's the other tricky part. I know, there's lots of tricks in this. You can't put a decimal in for x. So what do you think I'm going to do with the 64.964? Round. I'm going to go ahead and round up. Because they probably rounded the decimal. So I'm going to make that 65 out of 149. Okay, so if it doesn't give you an x, just put in the decimal and multiply it by your n value, and then round up. Now, this is your, it says prop and then not equal to less, this is your ha. So we're doing a less than, so you go over to less than and highlight it. Now, you can either calculate it or you can draw it. The drawing helps because it draws this again. And it just gives you a Z and a P. If you hit calculate, you don't see a picture, but it gives you all the information. So I'll do draw on this one, I'll do calculate on the other. So if you hit draw, see how there's my drawing, it should match this. This is your Z, this is your test statistic, it gives you a p-value. So yesterday I told you you had to look it up in a formula sheet. You don't have to. The calculator will give it to you. So this whole thing equals a negative 1.56. So that's what I got to put here. And then it gives me a p-value of 0.0598. So then just write it out like as a sentence. So a Z value of negative 1.56 gives us a p-value of 0.0598. Questions on this part? If it doesn't hit draw, you can always go back and just hit, this is what the calculate. The calculate will spit back out p hat. Don't get confused. This top one's your p-value. Okay. Questions so far? Like I said, this is the new stuff. Your conclusion, compare this to our alpha value. Remember, p is low, reject the ho. So is this less than 0.1? Yes. So for our conclusion, oops, can't see it. The first sentence should be, we're basically filling in the blank. Since the p-value of 0.0598 is less than our alpha, which equals 0.1, there is evidence to reject the claim that the proportion of 18 to 19-year-olds, so long sentence, who have been asked to buy cigarettes for an underage smoker is equal to 0.5. So like what I'm looking for is, do you reference your p-value, the alpha, this one's less than that one. I'm rejecting the claim, and then I use my condition 4 to kind of help fill in the sentence. Now the second sentence is, okay, so we rejected p equal 0.5, so now we're going with p is less than 0.5. So what does it actually mean? It appears that the true proportion is less than 0.5. Okay. So you want stat, and then you go to test number 5. That's the write-up. You just did your first one. Now, this one was real slow because I had to take you through it piece by piece. Again, you'll get faster at it the more you do it. This would be like one free response question on the AP test, and they say every free response question should take 10 to 15 minutes. So like your last test is 5 write-ups, so you have 52 minutes to do 5 write-ups, so that's like 10 minutes a piece. Okay. Let's do another one. Just so you have another example. Questions on the first one. Okay. So, according to the National Center for Health Statistics, 12.3% of all births in the U.S. were to teenagers in 1999. To see if this percentage has changed this year, a random sample of 1,000 births were investigated, and 111 were to teenage mothers. Using a significance level of 10%, can we conclude that the percentage of teenage births has changed? So again, the biggest thing I want you to make sure that you can do before you even start anything, make sure you know the difference between p and p hat. That 12.3%, that's your p-value. The 111 out of 1,000, that's your p hat. Okay. So we're going to use the 12.3 a lot more than the 0.11. So for the conditions, do you have a random sample? Yes. Now, if you didn't, because I think on the homework there's one that's not, you do what we did in Chapter 9. Not a random sample, proceed with caution. Stick with that. So p hat is from a random sample. So now I got to check n times p. So 0.123 times 1,000 is 123. That's greater than or equal to 10. And then I got to do the opposite. 0.877 times 1,000 is 877. That's greater than or equal to 10. So our sampling distribution is approximately normal by the central limit theorem. Again, if that didn't work out, proceed with caution. Keep going. Our only test is a 1 proportion z-test, and then p is the true proportion of U.S. births that were to teenagers. Sure. No, two. Oh, whatever. Doesn't matter. Okay, so your testing section. Remember, start with the ho and the ha, name it, draw it. So our null hypothesis, we think that P is equal to 0.123. And always change your percentages to decimals. The alternate, what's the question asking? Is it greater than, less than, or you think it's not equal? Not equal, because we're just looking at, has it changed? So P is not equal to 0.123. So this is what we call a two-tailed test. So your picture should have two of these, and you're going to get a negative and a positive Z. Now list everything. Basically anything you put in your calculator is what you should list. So here we were given an X value. It's 111. N was 1,000. So P hat's 0.111. Alpha here is 0.1. I think we're good. We'll do that later. So then your test statistic. Z equals, so here's where you take your P hat. So 0.111 minus 0.123 divided by the square root. 0.123 times 0.877 divided by 1,000. Now, again, you can calculate that. Yes.
So were those P and P hat in the testing, or
Just P hat. Because P is already up here.
If you're ready again,
No, I won't. I just crossed it out and write not needed. If you feel like it, you can. So, go to test 5. So again, P sub 0 is your ho and ha. So that's 0.123. Then I had 111 out of 1,000. And I'm doing a not equal. So you can, again, either hit calculate or draw. So do you see how like the area is wider? That's because our p-value is really big. So here we're going to fail to reject. So it gives you a z-value of a negative. So negative 1.16. And you can round to the nearest hundredth. P equals 0.2479. When you go back to put in your picture, do the positive 1.16 and the negative 1.16. I wrote it and said it backwards, but basically what they do is they take the probability of the negative and they multiply it by 2 because it's a two-tailed test. So a z value of negative 1.16 gives us a p-value of 0.2479. So like what this is 2 times, if I looked up, negative 1.16. 123. So it's 2 times whatever that is, because it's two-tailed. Okay. So our conclusion. Is this greater than or less than 0.1? Greater. So that means we fail to reject. So I'm giving you one of each kind of conclusion. So our conclusion. Oh, thank you. Since our p-value of 0.2479 is greater than our alpha of 0.1, we have evidence to fail to reject the claim that the true proportion of births in the U.S. to teenagers is 0.123. Now, you can write that much nicer than I can, but all I'm looking for is the p-value. Is it greater than or equal to your, or greater than or less than your alpha, and then what's your conclusion? Then this, again, comes from condition 4. So, we're failing to reject this, meaning we're kind of going with the null hypothesis. So, has the percentage changed in our conclusion? No. I mean, sure it has because this was like 20 years ago. But in this case, it has not changed. So, it appears the proportion of teenage births has not changed. Okay. And we always write it appears because, again, we're taking a sample and we're basing our conclusion on a sample. So when you're using the not equal to, just make sure you realize this is called a two-tailed test. When we're doing a two-sided test, a sample proportion above or below would give evidence against the null hypothesis. So when we calculate the p-value, we find the probability of getting the observed value in either direction. So we always take our p-value, you basically take your normal p-value and you multiply it by 2. Okay, if I were to go from a two-tailed test to a one-tailed test, I would cut my p-value in half. Not that I would really ask you to do that, but. Okay, questions on the write-up. I'll put this back up so you can see it.